Now I would like you to consider this exercise wherein this is a 32-bit string, and I want you people to convert this string into its decimal equivalent. Now how will you do that? So first of all, you will see the one which is there in the red, which means it is a sign bit because it is MSB, and when MSB is 0, which means the number is positive. Then we have 15 bits ka integer part. Then after that we have 16 bits fractional part. Now for the integer part, you will observe that there are preceding 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros to this number. Now if you now for calculating the decimal equivalent, you will only consider this part. Why? Because there are preceding zeros. These preceding zeros will have no value. Why? Because I will give you one example. If you want to buy a particular, let's say if you want to buy a Cadbury, which is of worth rupees 50. Okay. Do you say, so when I say 050 or 050, it is equivalent to 50. In the similar manner, if there are preceding zeros at the left hand side of the number integer part, then it is of no use. That is why we will be considering only this part, that is 101011, to convert it into its decimal equivalent. Now for for fractional part also, you will see there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13 zeros after the fractional part. After the fractional part. So here again these zeros are of no use. You will only consider 101. Okay. Now let us see the solution. How will you do that? So first of all, we will see the sign bit. Sign bit is 0. That means the number is positive. Then we will consider the integer part, which is this. Now out of this, as I have told you, we will only consider this part, that is 101011. Okay, because there are preceding zeros and these preceding zeros are of no use. Then how do we represent it? So see, I have written it as 1, 2, 4, 8, 16, 32. These are the weightages of these bits, and I have written the number as 101011. And for the fractional part also, let us see, prior to that, wherever there is 1, we have taken that number and added up. So here at 32 you will find 1, at 8 you will find 1, at 2 you will find 1, at 1 you will find 1. So we will add 32 plus 8 plus 2 plus 1, which becomes 43. This is for integer part. Now let us go for the fractional part. Now in fractional part, the fractional part is 101 and these many zeros. So you will have the value till these 3 bits only, because 1, 0 and 1. 0 raised to anything will be 0 only. So the actual value will be for these 3 values only. So when you calculate its decimal equivalent, how do you do that? So you do that by multiplying it into 2 raised to that particular exponent, and as we are to the right hand side, or we are calculating the decimal equivalent of fractional part, how it is calculated? So 1 into 2 raised to minus 1, 0 into 2 raised to minus 2, 1 into 10 raised to, or 1 into 2 raised to minus 3. So similarly 0.2 raised to minus 1 is 0.5, 2 raised to minus 2 is 0.75, 2 raised to minus 3 is 0.125. So when I calculate again these ones, what is the value, this one and this one? 0.5 plus 0.125 becomes 0.625. So when I add this up, this becomes 43.625. Sign bit is 0, therefore the number is 43.625. This is how we calculated. Now there are certain limitations of fixed point representation. Now what are these limitations? So the precision that we achieve in the result is less. Why it is less? I'll tell you. Also we can say the accuracy achieved is less. Now why? Let's say if you want to, you are performing one operation and you receive the result as 1010.1111. Now ideally you should store all these values. But then if you are using fixed point representation, I am pre-deciding the number of digits in the number, both integer part as well as the fractional part. So here if I decide that I want 4 digits in in integer part, and I want only 2 digits in the fractional part. So how will be the number stored in the computer's memory? It will be stored in the format of 1010.11. The other 2 bits, these 2 bits will be excluded because we have only given the limit of 2 bits for the fractional parts. So here, if I do not consider the next 2 bits into the calculation of results, I will get less accuracy, or I can say the precision is less. Therefore, these type of representations can be used in applications where precision loss will not cause an havoc. Or else I can give you one real-time example wherein you can say that these type of representations cannot be used in real-time applications. Now, what are real-time applications? Let us consider that you are traveling via aeroplane and pilot is communicating with the base station for the travel route in the air. We do not have roads in the air, so there are calculations to be made that take 45 degrees after this particular altitude, longitude, whatever. Now, if I consider fixed point representation and if I have given only 4 and 3 digits for integer as well as fractional part respectively, then it would lead to huge amount of error. Let's say if the actual value is 45 degrees, the pilot has to take turn at 45 degrees. With this type of storage and with this type of calculations, the pilot will receive the result which is inappropriate, inaccurate, and he may take turn at 43 degrees. Now, at the same time, from this opposite side, some other aeroplane is coming, so it would cause to accident, and in turn it would lead to huge loss of life. So these are the limitations of fixed point representation. Therefore, we move to floating point representation. Now for that, first we need to know what is floating point. So just observe, any number which has a point in it is called as a floating point number. Is it true or no? No, it is not. Why? So every point is not called as a floating point. Every point को floating point नहीं बोलते. Now how? Observe the following numbers. Let us consider this table. 73.2, 649, 0.2847, 5.63, and this particular column. Are all of them floating point numbers? What is the answer? The answer is no. Why? Now just observe this particular column. Here you will be able to see that the fixed point, or let's say the decimal point, or here we can say radix point, is fixed to one location. In all the numbers, the decimal point has been moved to only one location, that is after one first digit the decimal point is placed. That means, in the other words, we can also say that to the left hand side of the decimal point we have one non-zero digit. Yes or no? Yes. So this becomes fixed point numbers. Why? Because the dots or these radix points or these decimal points are having fixed location in the number, that is after first number. Now look at this particular column. 73.2, 649, 0.847, 5.63. What is this? Are the points fixed in this particular numbers? No, they are not fixed. That is why they are called as floating point numbers. They are moving from one place to other as the number is changing. That is why these are called as floating point numbers. Now what are the floating point numbers? Or else just look here. See here, 73.2, 649, 0.847, 5.63. Here the number is at this position. Then here in 649 the number is after 9, because 649 can be represented as 649.0 as well. 0.847 after the first digit decimal point is placed. 5.63 after the first digit decimal point is placed. So floating point numbers are the numbers wherein the position of the point is not fixed. Instead, it floats in the number. That means it moves in the number. Now, example 5 divided by 2, 2.5. 2 and 5 can be stored in the forms of zeros and ones, but this dot cannot be represented. So there must be some technique to represent these dots in the computer. So what are these techniques? So, or what is the solution? The solution is to convert floating point to fixed point. This process is called as normalization. Means what? And what is the rule of normalization? The rule says that there should be always one non-zero digit to the left of the point. There should be always one non-zero digit to the left of the point. Now, non-zero in decimal can be anything between 1 to 9 because one non-zero digit. One non-zero digit. When I say one non-zero digit means obviously 0 will not be considered, and from 1 to 9, 1 being the lowest and 9 being the highest. So, see, observe this particular table again. 73.2. This can be normalized or it can be converted into fixed point representation. When it is converted into fixed point representation, it is called as normalization. So the normalized form is, see what the rule is, to the left of the point there should be one non-zero digit. But here in this number, if you see, there are two non-zero digits. Therefore, we have to normalize it. So we shift this particular point one place to the left hand side. When I move this to the left hand side, I will increment the exponent by 1. Okay, now in 649, which is equivalent to 649.0. Now that means there are 3 numbers to the left of the decimal point. So what do? We shift it to one location. So it is decimal point to one location, that is 1 and 2. So exponent here is 2. Exponent is nothing but the number of places that you need to move, or it is also you can see in this particular for this particular number 0.847. Now when I say 0.847, here if you see to the left it is 0, but the rule of normalization is to the left hand side it should be always non-zero value. This is 0 value. So what we have to do is to make it to normalized form, what we do is we shift this particular dot to the right hand side, that is 8.47. Now if I make it if I am shifting the point to by one location to the right, which means the exponent will be incremented in the form of minus exponent. So here it will be 8.47 into 10 raised to minus 1. Similarly here 5.63 here the decimal point is at exact location, so there is no need of shifting the decimal point. So here that is why we have written in 10 raised to 0. Now here 10 is nothing but the base of the decimal system. That is why I have written 10. So I think I have made clear for the normalization rule. So the normalization rule says that to the left of the point there should be always one non-zero digit. Now let us look into floating point representation. So here the point has come to the fixed place. Now what we have done, we have normalized the number. In normalization we have done what? We have brought the decimal point just after one integer value. So here we have fixed the position of the radix point or decimal point. Now the point cannot be ignored. So this point cannot be ignored, otherwise the number will be saved in some other form. Therefore the point cannot be ignored. So after normalization, the number is stored in the form of s into m into 2 raised to e. What is n? Sine magnitude. What is sine? Sine is for this particular number. So let us calculate for this particular number, which is 5.6 into 10 raised to 0. What is the size of sign of this particular number? It is plus. Therefore the sign bit will be is equal to 0. 5.63. Now this 5.63, how do we do that? So see here, this 5.63 is nothing but the mantissa part, and 10 raised to 0 is nothing but exponent. Now what is mantissa? Mantissa is the digits of the number. So when I say 5.63, 5, 6 and 3 is the mantissa. When I say exponent 10 raised to 0, this tells the position of the point. We cannot store position of the point. We cannot store the point, but we can store its